In this lecture, we'll take a look at how computers use binary numbers to represent data.
We've previously talked about algorithms and doing computations and storing values in variables, but now we need to start taking a look at how those steps are actually done. So our first concern is, how do computers actually represent this information? So their internal storage techniques, or the way the data is stored in a machine, is very different from the way that we represent information whenever we write it or we note it or we do some type of calculation on paper. The way people normally would represent numbers and text would use the following notational conventions. So for numbers, we have 10 decimal digits, 0 through 9, to represent numeric values. For sign in numbers, we would normally include a plus sign or a minus sign in front of the number. If we're dealing with real numbers, we would have a decimal point that's included that would separate the whole number portion from the fractional portion of the number. And if we want to represent text, we have 26 letters of the alphabet, A through Z. Now, computers still use decimal digits and sign magnitude notation and the letters of the alphabet. They still use those, but the way that they're represented in the computer is using what we call binary numbers. So what we mean by a binary number is each digit is either 0 or 1. And this is different from a decimal number. A decimal number means that each digit is between 0 and 9. It could be any of those digits. But a binary number is either 0 or 1, and each digit is what we call a bit. So for example, we could have the binary number 111001, and each position in this binary number would correspond to a power of 2. So the rightmost number would correspond to 2 power 0. The second rightmost number would correspond to 2 power 1. The next one would correspond to 2 power 2. And so forth. If we want to evaluate a binary number, or in other words, convert a binary number into its decimal equivalent, then what we would do is we would multiply each 1 and 0 with the corresponding power of 2. And which power of 2 we use is based on where that 1 or that 0 is positioned. So once we have multiplied all of the respective values, we just simply add them all up, and that would give us our decimal equivalent. So let's take a look at an example. Let's use the 111001 binary number as our example. So what we're going to do is we're going to take each 1 and 0 and multiply it by a corresponding power of 2 based on the position. So the entire expression would look something like this. It would be 1 times 2 power 5 plus 1 times 2 power 4, plus 1 times 2 power 3, plus 0 times 2 power 2, plus 0 times 2 power 1, plus 1 times 2 power 0. So let me explain what's actually going on here. And to make it simpler, I think it'll be easier to go from right to left instead of left to right. So let's look at this first one right here. This one right here. This corresponds to the 1 times 2 power 0, and this is because the first position in a binary number corresponds to 2 power 0. So we take the 1 and we multiply it by the 2 power 0, and well, 2 power 0 is 1, so that gives us 1 times 1, so this part right here gives us the 1 part of our total value. Now let's take a look at the second digit, so this 0 right here. This 0 corresponds to the second binary number, so that's going to be 2 power 1. So that's where we get this 0 times 2 power 1 right here. Well, that's going to be 0. So then we can take a look at the next binary digit, or bit, I should say. So this corresponds to 2 power 2. So this is where we get 0 times 2 power 2. And, well, that's going to give us 0. So then we move on to the next bit. So we go to this one right here. And that corresponds to position 2 power 3. So we're going to compute 1 times 2 power 3 right here. And 2 power 3 is 8. So 8 times 1 is sure enough 8. So 8 is going to be parts of our value that we end up adding. We then go to the next bit. So we go to the next one right here. So this corresponds to 2 power 4. So this is where we get 1 times 2 power 4. 2 power 4 is 16, so 1 times 16, that gives us 16. And then finally, we go to this last one right here. So this corresponds to 2 power 5, so that's where we get this product right here. So 1 times 2 power 5, well, 2 power 5 is 32, so we get 32. So sure enough, we do all these multiplications, and then we add them all up. So we get the 32, the 16, the 8, the 0, and the 1. So if we add all that up, this would give us 57, which is the decimal equivalent of 111001. So we can do this for any binary number. In fact, we can actually extend this for other bases. We just have to change the 2 to be whatever base we're dealing with. But we're not going to worry about that in this class. We're only going to worry about binary numbers. Now, there is a second way that we can go about converting a binary number into its decimal equivalent. Because all we have to recognize is we just need to take the positional values of the ones digits and then just add up those positional values. Because notice that for the 2 zeros, we didn't add them to our sum. So the 2 power 2, the 2 power 1, those weren't included in our sum. So we only need to take a look at the positions that have ones, take those 2 power whatever they are, and then add them all up. So in this example, all we had to do is just take 2 power 5, 2 power 4, 2 power 3, and 2 power 0, add them all up, and that would also give us our value. Let's have you do a different example just to make sure you got the hang of converting a binary number into a decimal number. So here we'll do 10111. So pause the video, work it out, and then resume the video once you're pretty sure you have the answer. Okay, so the only thing here to note is that the second number to the left, or technically the fourth number to the right, is a 0 and everything else is 1. So when we do the computation, this is going to be 1 times 2 to the 4th power, plus 0 times 2 to the 3rd power, plus 1 times 2 to the 2nd power, plus 1 times 2 to the 1st power, plus 1 times 2 to the 0th power. So this comes out to 16 plus 0 plus 4 plus 2 plus 1. So if we add all that up, we would get 23 as our answer. Here is an example table of all of the binary and corresponding decimal values from values 0 all the way to 15. So you can try out the algorithm for converting from binary to decimal just to make sure that you have a good feel for how these work. In fact, for some of these smaller values, it might even be easier just to memorize some of the binary values and to determine the decimal equivalent. But take a couple minutes to read over this list, take some notes, and you can just kind of see the pattern for incrementing binary values and see the decimal equivalents of them. Let's take a look at how we would convert a decimal number into binary. The main idea is that we're going to repeatedly divide the number by 2. So we'll take the original number, divide it by 2, which means that the remainder is going to be either 0 or 1. So we'll record this remainder, and then we'll take the quotient and divide that by 2. And we're just going to keep repeating this. We'll record the remainder, and then we'll divide that quotient by 2. We'll record and just keep doing this until the quotient becomes 0. So once we've done this, the sequence of the remainder digits, so all those remainders that we wrote down, if we write them left to right from the last remainder to the first remainder, this gives us the binary number. Let's do an example where we would convert 19 into binary. So we'll start by taking 19 and dividing it by 2. So that means we get a quotient of 9 and the remainder is 1. So we'll just take note of the remainder. We'll then take the quotient and divide it by 2. So 9 divided by 2 is going to give us 4, with the remainder of that being 1. We then take the quotient again and divide it by 2. So that means the quotient is going to be 2 and the remainder is 0. So then we'll take the quotient of that, divide it by 2. So we get a quotient of 1 and the remainder is going to be 0. And then finally, we'll take that quotient, which is 1, divide it by 2. We get a quotient of 0, which means we're done dividing, and then the remainder is going to be 1. We now read the remainders in order from the last remainder to the first one. So that means that our binary number is going to be 1, 0, 1, 1. In every computer, there is a maximum number of binary digits that can be used to store an integer. Now, typically this value is going to be either 16, 32, or 64 bits. But once we have determined this maximum number, it will also give us the largest unsigned whole number that can be represented in the computer. So for example, let's say we use 16 bits for storing the largest possible value. So the largest integer that we can store, is 116 times, which turns out to be 65,535. So the whole point here is unsigned integers larger than this cannot be represented with 16 binary digits. So we wouldn't be able to assign any values larger than this. Let's talk about how we would add binary numbers. We're actually going to use the same rules that we use for adding decimals. The only difference is 1 plus 1 is now 10 instead of 2, because 2 is not a valid digit in the binary system. So we're going to go old school. We're going to use grade school techniques to add the numbers, and then we're going to carry the 1 digit whenever we need to. So here's an example where we would add 00111 with 01110. Now, if you don't know what those values are, those are adding 7 and 14. So we'll eventually get 21, but we'll take a look at the process of how we would add these digits. And notice that the way they're set up is we're pretty much setting up just like we do with grade school math, where we take one number over the other, and we're going to add the numbers 1 bit or 1 digit at a time. So the first step is we're going to do the 1 and 0 on the far right. Well, 1 plus 0 is going to be 1. And then our carry bit, well, it's going to be 0 because we didn't get 1 and 1. If we get 1 and 1, then we would carry a 1, but here the carry bit is going to be 0. We'll now add the second set of bits. So 1 plus 1 is going to be 10. So we leave the 0 at the bottom, and then we'll carry the 1 over to the next place in our number. So we now are adding 1 plus 1 plus 1, and that gives us the binary number 1, 1. So the right portion of the 1, that right one, will stay at the bottom, so that's going to be part of our sum. And then the other one is going to be our carry bit over to the next place. We then add the 1, 0, and 1, so that gives us 0 because 1 plus 1 is 1, 0. And then we carry a 1 over to the next place. We then add 1 with 0 and 0, and that just gives us a 1. So our final result is 10101, which is the binary value 21.